So, welcome back to our continued discussion on vortex dynamics. So, in previous lecture, uh, we arrived at the evolution equation for vorticity. So, we saw that the evolution of vorticity is governed by the Helmholtz equation. Which requires us to make the following assumption, that the fluid is inviscid. You have conservative body forces, case in point being gravity. We are also assuming that the fluid is barotropic. So, we saw that there is a possibility of a torque of the form like grad P cross grad rho, and if the fluid is barotropic, which means that pressure is purely a function of density, then this particular term vanishes, and so the baroclinic source of vorticity is not there. And here we haven't made any comment regarding incompressibility, which means that the Helmholtz equation needs to be seen in conjunction with our equation of continuity. So, now if I combine the two equations, I can write after a little bit of algebra in the following form. So, what we have here is the material derivative of vorticity by density obeys this particular equation, once again sticking to the assumptions that we made. Now, this is a vorticity equation that is applicable even if the fluid was not incompressible. If I were to be dealing with an incompressible system, it gets simplified, but otherwise we have a form here which allows for there being non-zero divergence for the velocity field. Now, this brings about a few, so there are few things which we can learn from the evolution of vorticity. So, we will do it first exploring the equation which is for an arbitrary system, and then we will go back to our pure vorticity equation without the density part and try to understand those individually term by term. So, this equation, the equation that we have written down for the vorticity, places certain conditions or constraints. So, we have some conditions or constraints on how vorticity would evolve in a problem, and this incidentally came almost a decade before Kelvin circulation theorem, which are known as Helmholtz vortex theorems. There are different ways of writing what the Helmholtz vortex theorems are. I will write them in primarily three ways what we can infer from this equation. The first statement for Helmholtz vortex theorem is that if initially region was free of vorticity, it continues to be free of vorticity for all time. So, if there are fluid particles are initially devoid of vorticity, they continue to be free of vorticity forever. And the simple way is to just, if we look at this particular equation, this is an equation which is evolution in time following a fluid particle, ddt of omega by rho is equal to omega by rho dot del u. So, it is an initial value problem in vorticity. So, if you say that I did not have any vorticity to begin with, so if you just either see it in a formal sense or you see it in more like a numerical sense. If you see it more like a numerical sense, if you have to solve this, the LHS, and you do a time stepping saying that I want to find out what is omega at time t plus delta t given the value of omega at time t, then the RHS is exactly 0 at t equals 0 if there was no initial vorticity, which means that initially if it was devoid of vorticity, it continues to remain devoid of vorticity. It will not be creating any vorticity by itself. The second theorem is that if fluid particles lie on a vortex line, they would remain on that vortex line. So, it is like almost they are getting pinned to that particular vortex line. If there were fluid particles which were residing on a particular vortex line, they remain on that vortex line forever. So, this is something again consistent with what we have seen. If you remember, we had a statement that if I have a small line element, how does that small segment evolve? So, the evolution of that small segment was ddt of, let us say, a delta s, which is that line element, is going to evolve as delta s dot del u. This is basically how we had defined velocity gradient. When we were trying to actually explain what velocity gradients are, we said that consider 2 points in the fluid separated by a particular distance, let us say delta s here, and then how would that distance evolve in time? The distance would evolve in time because of the velocity gradient. That is how we came up with the idea of a velocity gradient. The two neighboring points, they basically would have a difference in velocity which would be captured by the velocity gradient. That is our starting place of that equation. So, now if I were to subtract equation 2 from equation 1, then I have ddt of omega by rho minus delta s is omega by rho minus delta s dot del u. So, what this is telling us is that if there was a vortex line and I consider a segment of fluid particle which is residing on that vortex line. So, that is delta s, it is coincident with omega, right. It is basically exactly pointing in the same direction or lying on that vortex line. So, then if that is the case, it will continue to be so forever. It is not going to move, it is not going to detach away from that vortex line. So, if you have some fluid particles which are on a vortex line, they continue to remain on that vortex line. And the third statement of Helmholtz vortex theorem is that if you consider a circuit of fluid and you find the strength of the vortex, that remains unchanged in time. Now, this we have already encountered. We have already done this before, which was a restatement of Kelvin circulation theorem. That if you consider a circuit, a patch, and you have basically found the strength of the vorticity, it remains the same for all time. That strength does not change, the strength of that patch, or in other words, if I were to think of a cross section and draw a bunch of vortex lines. So, imagine that you have created this surface which is threaded by vortex lines. Just like we discussed a concept of a stream tube, this is a vortex tube. So, what this says is that the strength of that vortex tube does not change with time. The tube will do a lot of different things. The tube is not going to remain identical in shape and form. It can contract, it can expand, it can bend, it can develop a lot of different things. One thing which will not happen is that the strength of that vortex tube is not going to change. So, this is primarily what gives us a guidance regarding how vorticity is going to evolve. The other point, which is in a sense regarding how vortex lines are going to be, is that vortex lines can never terminate in the fluid. What does that mean? It means that either they form closed loops like a vortex ring, or they end in a boundary, solid or free surface. We have done interfaces earlier in boundary condition. So, a vortex line will not just abruptly end in a fluid. If you are tracking a vortex line and you are basically looking at how a vortex line is evolving, the vortex line can come and close onto itself and form a loop or a closed ring. That is a vortex ring. It need not be circular, it can be of any shape, but it can be closed. The other possibility is that the vortex line comes and terminates on a solid boundary or a free surface. Else the vortex line has to extend from infinity to infinity. If in a domain, it will not be able to terminate. There is one more assumption which you have made here, which I have not said. So, I have listed out the three primary assumptions that went into saying how we arrived at this, is that the fluid is inviscid, the fluid has no effects of any non-conservative forces, and also the fact that the system is barotropic. There is one more assumption I have made, and I have not listed it because we have not discussed it in our formulation, is that this is in a non-rotating frame of reference. Whatever we are studying here, we are studying in a non-rotating frame of reference. At some point later, we will discuss about how the equations of motions are going to change, and thus how vorticity equation will change if we are in a background that is rotating. And the simplest example of this is any fluid mechanics that you are studying on the surface of Earth. Earth is a rotating background. So, if you are trying to study the evolution of vorticity on the surface of Earth, obviously you have a rotating background. So, everything that we are discussing, starting from a circulation theorem, including the effects of how vortex lines behave, all of these things need to be modified. Your equation for vorticity needs to be modified. So, we will not dwell on that right now, we will come back towards this in the end, but it is important to understand that every derivation that we have done in a frame of reference that is inertial. The moment you are studying fluid mechanics in a non-inertial frame of references, you have to account for these additional contributions that will come in, contributions like Coriolis force, which is not there in this current picture. So, we will not complicate it right now with any discussion on rotating background, but that is an important point to keep in mind. So, with these pictures, it's quite important to emphasize that studying through vorticity is a very useful way of understanding what is happening to the flow. As I said, that the non-local relationship between velocity and vorticity, that given vorticity how you get the velocity, implies that you can actually study the vortices by themselves, and that is sufficient for you to understand what is going on in the flow. So, it is quite economical to study using vorticity. It also is on occasions methods gives us computational methods. That you are developing computational methods to study fluid mechanics. There are methods which are built on using this idea. Vortex methods, where you actually develop methods in studying the problem based on evolution of vorticity. Because you saw that the evolution of vorticity, and especially under the setting that we are doing, is governed by this equation. So, if you make a further simplification, and let us say you are doing a constant density problem. So, if you do a constant density problem, then the vorticity equation is, it is the following: ddt of omega, where ddt is dou dot t plus u dot del. So, the material derivative of the vorticity is omega dot del u. It's a very simple equation, and you can develop numerical methods, because here you are not tracking pressure explicitly. You are not tracking any other variable, you are only tracking for vorticity, but there is a small detail which I am kind of skipping over. You cannot just solve this equation as only a function of vorticity. There is also a velocity there, and vorticity and velocity are related to each other. So, if you were to write the expression, then we know that vorticity is curl of velocity, and we saw the inversion in previous class using Biot-Savart. So, if you have to solve this equation, you also need to know the velocity field associated with that vorticity. So, it's not trivial, but definitely it's a neat way of addressing and understanding a problem, and you can develop numerical methods that are based on solving this equation. And this equation becomes significantly simple if you were to do 2D. So, we are now doing incompressible. So, everything we will do now forward is for incompressible flows. So, for incompressible flows, we are already assuming that velocity is divergence free. So, if I do 2D flows, what happens to the right hand side? Omega dot del u. So, u will have an x component, a y component, and no z component. And we are also saying that the flow does not vary in the z direction, which means your vorticity, so u is a function of x and y, v or and t, x, y and t, v is a function of x, y and t, and vorticity is only in the z direction. There is a single component of vorticity which is a function of x and y and t, and there are two components of velocity, u and v. Now, what does it do for this particular term omega dot del u? Omega is only in the z direction, which means this is omega dou z of u. Ideally, omega dot del in Cartesian coordinate would be omega x dou x plus omega y dou y plus omega z dou z. If the flow is two dimensional, these terms are not there, you are only left with one single term, a flow that resides in the xy plane and varies only in the xy direction. So, you only have omega dou z of the velocity field, but the velocity field is only a function of x, y and t, which means this term is identically 0. So, for two dimensional flows, your vorticity equation becomes this. Now, this is really a very neat equation to understand what is happening to vorticity. So, when you are thinking of a flow that is purely two dimensional, vorticity basically remains advected purely by along the fluid particle, and all you are saying is ddt of omega is equal to 0. Now, if you write this out explicitly, you have dou t u dot del omega is equal to 0. But omega only has a single component, so I can just write omega as in terms of its component. And we know if the flow is two dimensional and incompressible, we can define a stream function. where u is dou psi dou y and v is minus dou psi dou x. So, the equation that we have is dou t u dot del omega is equal to 0, and we have u as dou psi dou y, v as minus dou psi dou x, omega is dou v dou x minus dou u dou y. So, this is minus dou square dou x square of psi minus dou square dou y square of psi. So, for a 2D incompressible flow, the vorticity is negative Laplacian of the stream function. And u dot del, if I write this out explicitly, this is u dou dou x plus v dou dou y. So, now what this gives us is dou psi dou y dou dou x minus dou psi dou x dou dou y. So, eventually the equation that you have is dou dou t omega plus u dot del omega is equal to 0. If I now substitute, I get minus dou dou t of del square psi plus dou psi dou y dou dou x minus dou psi dou x dou dou y of minus del square psi is equal to 0. So, we have now an equation which is dou dou t of del square psi plus dou psi dou y dou dou x del square psi minus dou psi dou x dou dou y del square psi is equal to 0. So, this is an equation now which is purely in terms of stream function. This is the part which we had commented, that the advantage of introducing stream function in 2D is you are now able to write down an equation purely in terms of one single function, which is the stream function. So, that actually is coming from the vorticity, which is why often when you are solving two-dimensional flows numerically, there are methods which basically use what is known as the vorticity stream function method, that you are actually solving it in terms of vorticity and stream function. So, these are vorticity, and then obviously I am relating vorticity in terms of stream function using the Laplacian. And you can go further and it gets quite interesting. If you say that I am interested in steady flows, so what have you said? 2D incompressible steady flows, and obviously you are ignoring viscous effects. So, 2D incompressible inviscid steady flows. If I say that, then the only thing that survives is dou psi dou y dou dou x del square psi minus dou psi dou x dou dou y del square psi is equal to 0. This is an exact nonlinear formulation that you have now. And as you can see that if del square psi or vorticity, so del square psi is negative of vorticity, if this was some functional of stream function, functional of stream function means it is a function where the variable is the stream function. What happens to the equation? If del square psi was some f of psi, take an example, let us say that del square psi was psi. If del square psi is equal to psi, then dou dou x of psi would be dou psi dou x, dou dou y of del square psi would be dou psi dou y. What happens to the term inside the bracket? It gets exactly satisfied. So, if del square psi is a function of psi, so if vorticity is a functional of the stream function, then the relation that we wrote down if I now plug it in, dou psi dou y is f dash psi dou psi dou x minus dou psi dou x f dash psi dou psi dou y. So, it trivially gets satisfied, which means this is a solution of your 2D steady incompressible inviscid equations. It is a nonlinear solution. I did not drop anything about the linearity. So, there are very few ways of coming up with nonlinear solutions of your governing equation, and this is one solution. So, what it says is that your vorticity is a functional of the stream function. Now, you can choose various forms of vorticity, the functional. So, you can say f of psi is psi. You can choose f of psi as some exponential of psi. You can choose various functions and you can play around with this, and you will generate various steady flow patterns which are exact solutions. Now, some of them may just be abstract mathematical entities, but others are actually related to what a flow profile looks like. So, several of these actually give you very nice description of real flow phenomena, of what it actually looks like. So, this is a scenario where you now have understanding what is going on in a 2D steady inviscid incompressible flow. But if you did not have all of that, you would be back to solving this particular equation. But this picture is actually more interesting when you do 3D. So, going back to the equation that we had in 3D, so the other assumptions remain the same. So, it is inviscid, it is incompressible. The equation that we have there is dou omega dou t is equal to omega dot del u. So, what you see in 3D is that there is some kind of a source term. It appears like a generation of vorticity kind of a term. Now, it is not really a vorticity generation rather than rearrangement of vorticity from one to the other. So, how do we understand this particular term? We know this term is 0 for purely two-dimensional flows and it is non-zero for 3D flows. So, what does this term actually represent? So, let us consider a vortex line. And at a particular point, I am going to draw a local axis. So, I am just drawing a local x, y, z axis such that the vorticity line is tangent to the z axis at that particular point. The vorticity line is some arbitrary line, but at that particular point where I have drawn the axis, I can write locally my vorticity as 0, 0 omega. I am just saying that this particular term has a component that is only in the z direction. Otherwise, the vortex line is some arbitrary shaped, but at some particular point I have designed a coordinate system where the z axis is the tangent. So, if the z axis is the tangent to the vortex line, that means that the only component of vorticity that will exist will be along the tangent. The other components will not exist at that particular point. So, this is a local coordinate system that I have designed. So, if I write this term out, omega dot del u, this would be omega dou u dou x, sorry, it will be omega dou u dou z plus dou v dou z plus omega dou w dou z, because omega only has a component in the z direction, in that local tangent coordinate system. So, it is only going to give you a term that is omega dou z, it will not give you any other term. So, now if I want to understand these terms separately, let us try to understand each of these terms separately. So, I have omega dou u dou x. Now, this, because if you write this down, so actually I should have, this is a vector. So, here this is in the x direction, this is in the y direction, this is in the z direction. So, if I write this down in the RHS, so LHS is d omega dt. So, which will have terms like dou t plus u dot del acting on omega x, x cap, the same thing omega y, y cap, the same thing omega z, z cap. And on the RHS, we have a term which is omega, which is the z component, dou u dou z. Here it is omega dou v dou z. So, what this tells us is that if you have a flow there is a change in your vorticity. So, initially at that particular location there was no x and y vorticity. If you go back to the configuration that we had, we drew this kind of a tangent coordinate system. At that particular location the vorticity was, so here x, y, z is defined as that local tangent and normal coordinate system. So, at that particular location, at the instant I am considering this, there was no vorticity that was in the normal direction, in the x or the y direction, it was purely tangential. Now, if dou z of u is non-zero, what it does, it creates a vorticity in the x direction. So, you have a generation of x vorticity, which if you write it in a small time interval delta t, will be the following. So, there is a delta omega x that you are creating in a small time snapshot, that is due to the vorticity that was there at that location in the z direction coupled with the variation of the x velocity along the z direction. This is quite similar to think of it like if you have a flow like this. So, if this was my z and x, so I have a shear flow here where the flow is in the x direction, it varies in the z direction. So, which means dou u dou z. So, the velocity field is u, a function of z in the x direction. So, dou u dou z is non-zero. So, if you think of a line of die here, what happens to the line of die? The line of die was initially vertical, aligned with the z axis. Because of this shear that you have, the line of die gets tilted, it is going to tilt. As it tilts, the line of die, if you were to project, it will have a projection along the x axis as well as the z axis. That initial line of die that you had was purely along the z direction. Because of the flow, the line of die got tilted, and now the die is an oblique die at some point because of that shear, which then gives you that if you were to try to find out that if you think of it in terms of a small line vector, then that line vector actually has a projection along x as well as his original z. So, similarly, the vorticity line which at that location was purely tangential or along that z direction got tilted by the shear dou u dou z, and you generated a vorticity in the x direction. So the vortex line is present. There is a shear flow that is there. So velocity here, u velocity does vary along the z direction. So you can think of at this location, if you have a x velocity that is varying along the z direction, it tilts the vortex line. The moment it tilts the vortex line, it creates automatically a vorticity that was initially absent. Initially there was no vorticity in the x direction, it was purely 0. In the same fashion, initially there was no vorticity along the y direction, and you create that vorticity due to the fact that, so I draw the line, I draw my z, x and y. So there is a flow, now there is a shear flow in the y direction which is varying in the z. So if there is a shear flow in the yz plane, so it is in the y direction, there is a v velocity which is varying in the z direction, it will tilt that vorticity and generate a vorticity in the y direction which was earlier absent. So at time t equal to 0, your vorticity at that location purely in that local coordinate sense only had a z component. Immediately at the next time snapshot, the shear, the local shear that is present there, shear basically is the velocity gradient. So because of that local velocity gradient at that location, it is going to tilt that vortex line, and the moment the vortex line gets tilted, it is automatically creating components of vorticity in the other direction. So that is a source of how vorticity gets generated. So none of your statements regarding circulation, strength of vortex tube gets altered, nothing changes here. But what is happening is, because of the flow, your vorticity from one direction gets created into some other direction because of the local shear. So the coupling of the shear and the initial vorticity gives you a possibility of creating additional vorticity in other direction. So this is a mechanism which is known as tilting of vortex lines. So whenever vortex line gets tilted, it automatically creates, just like a line element when it gets tilted, you automatically have a projection of that line element vector on the other directions the moment it gets tilted. Similarly, whenever a vortex line gets tilted, there is a component of vorticity that is getting created in the other direction. What leads to the tilting is the velocity gradient or the shear at that location. So that was regarding the parts which are in x and y. But there is also another part which is omega dou w dou z, z hat. Now how do I understand this particular term? Now since I am dealing with an incompressible flow, dou z of w can be written as negative of dou u dou x plus dou v dou y. So I have a three-dimensional flow, and this particular quantity, what would this represent? It is the 2D divergence. Even though the flow is incompressible, this is not necessarily 0. In a general three-dimensional flow, there is no guarantee that it has to be 0. What this gives us, it gives us a measure. If you remember, when we discussed divergence, what did we say? That divergence of the velocity field was related to, or minus of divergence of the velocity field was related to del v ddt of del v. That volume elements are basically evolving based on the divergence that is there. If you have a positive, so if del dot u was positive, so I am basically having a scenario where if I have, so I think let me just check the sign 1 minute. Yeah, so this should be plus. So if I have a positive divergence, that means my volume is going to increase. If I have a convergence, then my volume is going to decrease. Now we are dealing with incompressible flow, which means volume is not changing or is not increasing or decreasing. Volume elements are, infinitesimal volume elements are remaining preserved. But if I do this for the two-dimensional counterpart, then this would be the area element. In a 2D problem, the rate of change of area is related to the divergence of that 2D velocity field. Now, this is dou u dou x plus dou v dou y. Volume is not going to change, but the areas can increase or decrease, right. I can think of a cube which is basically going to always have the same volume, but it can become a cuboid of different aspect ratio. It can become any other shape, and by doing so, it is constantly changing its surface areas, or it is one particular surface area is constantly changing. So there is no constriction on the how the area changes. So what this gives us is that from the z component, del omega z is omega dou z omega dou w dou z del t, which is minus omega dou u dou x plus dou v dou y del t, which is minus omega the rate of so omega del t 1 by delta A ddt, sorry, delta A ddt delta A. So this tells us that you can generate vorticity by having the cross-sectional area of the vortex tube change. If ddt of delta A were to increase, so ddt of the cross-sectional area were to go up, then the right hand side is becoming negative, which means your vertical velocity del omega z is going to get reduced. So if you have the vortex tube becoming bigger, cross-sectional size increases, it is effectively now going to have lower vorticity. Similarly, if you now have the cross-sectional area going down, which means that the rate is negative, it is shrinking in size, then the right hand side now becomes positive, which implies that I need to get higher vorticity or an increase in vorticity. So this you can imagine that I have a vortex tube which has, I am just drawing for the sake of keeping things simple, it only has a vorticity that is pointing along this axis. So it is threaded by a lot of these vortex lines. Now if this vortex tubes gets bigger in its cross-sectional size, then the vorticity that you will have is going to be higher than what it was earlier. Sorry, it should be lower. So it should be lower than what it was earlier. it's going to spin slower. You understand vorticity as a measure of your spin. So, you have a vortex tube which is spinning with a certain vorticity. As it gets bigger, it has to now spin slower. If it were to get narrower, then it should now spin faster. So, this is now why is it basically getting narrower and why is it getting fatter? That is because you have omega dou w dou z. Now, what is dou w dou z? We wrote it in terms of the 2D divergence, but dou w dou z is basically a vertical velocity or the z component velocity that is varying in the z direction. So, imagine that the vortex tube is being stretched. If the vortex tube gets stretched, it gets thinner. You have a pipe, you are stretching the pipe, the volume has to remain conserved. So, as you stretch it, its cross-sectional area shrinks. Now, if you think of exactly this being mapped to a vortex tube, the tube basically gets of smaller cross-sectional radius and thus now it has to start spinning much faster. Similarly, this stretching exercise, if it were to actually compress the vortex tube. So, you have a flow that is kind of compressing it. So, I fatten the tube. The tube basically becomes much bigger in size because I am trying to push it, I am trying to compress it. So, when I am trying to compress it, when there is a vertical velocity dou z of w which is running towards the origin, it is basically trying to push things inward, it will create a scenario where the vortex tube now gets wider and thus it has to start spinning slower. So, what we saw is that in the vorticity equation we had this particular term. When we split this term out and we write it in terms of the contribution that we get from the x, if you do it in terms of a local, okay, if you do it in terms of a local coordinate system, there is going to be a part that will come from tilting and there will be a part that will come from stretching. So, you can rearrange your vorticity by the flow and it can lead to stretching and tilting, and stretching and tilting is basically going to be responsible for transfer of vorticity from one component to the other or increase or decrease of vorticity. And this plays a huge role in a general three-dimensional flow, especially in turbulent flows. Because you have to understand that I have kind of explained this as if the velocity and vorticity are decoupled from each other. They are not decoupled from each other, they are coupled. The velocity field and vorticity field, there is no causal relationship, there is a kinematic relationship. The curl of the velocity field is the vorticity field. So, now the point is that the vorticity that is there in the problem is associated with the velocity field, and if this velocity field, so you can think of your turbulence as an array of many such vortex tubes. I am drawing all of them parallel, but there will never be such nice stacks of vortices that you have. But if you just think of this cartoon, that I have these kind of array of these vortex tubes which are there, which is in a bath of a flow. Now, what the flow is trying to do, it is constantly trying to stretch these tubes, tilt these tubes. So, effectively the stretching and tilting of these tubes will basically create additional components of vorticity, which will then have a feedback and create additional velocity component associated with the tube. Because each of these tubes, if the tube was exactly of this particular kind, which means that they were all axial in nature, in which case they are going to drive a flow. And now you can think of one of these tubes in a sea of velocity field that is created by all the other tubes. So, it is getting stretched, it is getting tilted. The moment it gets stretched and tilted, it will basically depart from its configuration. It can spin faster, it can tilt and create other vorticity. So, this constantly keeps happening. The stretching and tilting is what is constantly playing a role in how vorticity gets rearranged in the problem. So, this is the story of what vorticity does and how vorticity gets transferred or changed in a problem. The generation of vorticity, which we saw, there is a possibility through baroclinic torque. But one important thing which we have ignored in all of this, which has been our constant assumption, that this is all being done ignoring effects of viscosity. We have learned the Navier-Stokes equation. So, the term that was here for which we took a curl, that was curl of mu by rho del square u. That is the term which we did not take into account. So, if I am just thinking of this problem as a constant density fluid, then mu by rho is a constant and it is known as the kinematic viscosity, and what you have is nu del square del cross del square u. If I commute these two derivatives, I get nu del square omega. So, we will do this at some point in detail, basically looking at the viscous diffusion part. So, everything that we are discussing here is ignoring the aspect of diffusion of vorticity. We learnt about diffusion of momentum. Now, there is going to be associated with that a diffusion of vorticity, and we will see what that does in terms of our evolution. So, to summarize, we saw that vorticity, which is the curl of the velocity field, associated with that we came across with the quantity that is circulation, and we learnt about Kelvin circulation theorem, which says that if I have a barotropic fluid, this is a new term that we learnt, which is basically pressure being purely a function of density. If I have an inviscid barotropic fluid with conservative body forces, then if I know what is the strength of that vortex tube over a particular contour, as this contour evolves in the flow and it takes some other shape, circulation should remain conserved. Then we encountered the aspect of how we invert this and write it using the Biot-Savart relationship. So, that is basically how velocity or the vertical part of the velocity is related to the vorticity. We also came across the vorticity equation, where there was a new term that we encountered known as the baroclinic torque. There is an additional two terms which are quite different from how just an evolution occurs. So, when we again considered a barotropic fluid, we came across the three theorems of Helmholtz, and finally what we saw is that if we consider this to be further an incompressible flow, there is a stretching and tilting mechanism that is at play. We have also encountered examples of simple vortex configuration. So, we did a solid body rotation, which was u was omega r theta cap and omega was 2 omega z cap. We also saw a point vortex where u was gamma by 2 pi r theta cap. Vorticity is actually 0 everywhere other than at one particular location. And the point vortex, which we said that there is one single point which drives a flow. So, the velocity is gamma by 2 pi r. So, if I say this has a plus gamma, then the sense of motion is going to be anti-clockwise. Now, if you have another point vortex which is at some other distance, that is also going to drive a velocity which is gamma by 2 pi r. And I leave it here as an exercise for you to think what would happen to these 2 point vortices, which are in one case both have the same sense of rotation, and in the other case where they have an opposite sense of rotation. So, this is plus gamma, this is minus gamma. So, this is a simple problem that you can think in terms of how vortices are going to interact with each other. So, I leave this as an example or something to think about. I will discuss this briefly before next class, that how would these vortices interact given that they spin in the same sense or they spin in the opposite sense. Thank you.